Exercise 228 introduces the fourth pattern of resonance. And that pattern is when you have a pi bond. Remember, a pi bond is every bond after the first bond. So if you have a double or a triple bond between two atoms of differing electronegativity. Remember, electronegativity is how much a nucleus attracts electrons. It increases valence electrons, and it increases as you go up and to the right. So in the top right, you have nitrogen, oxygen, fluorine, and chlorine. Those are the most electronegative atoms on the periodic table. They pull electrons to themselves and leave the atoms they're bonded to with a slight positive charge. And so those atoms are usually going to show up in this resonance structure because that's what they mean when you're saying different electronegativity. You have those nitrogen, oxygen, fluorine, and chlorines that have a gigantic electronegativity and other stuff that has a much lower electronegativity. I should note sometimes also underneath the chlorine, if you keep going down, it's bromine and iodine. Sometimes those are treated as being pretty electronegative too. They're not as big as these heavy hitters right here, but they are significant, so just keep that in the back of your mind. Okay, so here we have a pi bond between atoms of different electronegativity. It's this bond right here. Nitrogen, very electronegative, and carbon, not as electronegative. Every bond after the first bond is a pi bond. So we have a pi bond between atoms of different electronegativity, and so we have resonance. So draw those brackets that warn the world about the resonance that's about to happen, that all these structures in here none of them represent the real molecule. The real molecule is only the average of all of the structures inside. And so you draw that special resonance arrow with the two heads and the one line. Okay, well, first, just as good practice, best practices type thing, draw in the lone pairs. None of the carbons here have a negative charge, so carbon doesn't have a lone pair. This nitrogen already has 6 electrons around it, so we just add 2 more for a lone pair, right? Because remember, each bond has 2, so 2, 4, 6 electrons. 8 plus the lone pair. Trying to get all the atoms to have 8 electrons. So that is our structure, and then what you see as the curved arrow pattern here is that the electrons go toward the more electronegative atom. And that should make sense. That's what electronegativity means, that an atom really attracts those valence electrons in bonds. So the electrons go toward the more electronegative atom. So you copy the structure exactly as it is. And I'll even put in that arrow there. Wherever you have the tail of an arrow, that's where electrons are moving away from, so you erase those. And wherever you have the head of an arrow, wherever that's pointing, that's where electrons are arriving, so you draw electrons in. If an arrow points at an atom, then the electrons arrive as a lone pair. Now we just want to think about formal charge. The nitrogen is in group 5a, so 5 minus, that has 4 dots and 2 lines around it. So that's 5 minus 6, or negative 1. So there's a negative 1 charge around the nitrogen. And this carbon, notice it has 0 hydrogens, because it has 1, 2, 3, 4 bonds. That means it has 0 hydrogens in it, 4 bonds to other stuff. So 4 minus, we have 0 dots here, and 3 lines. 4 minus 3 is positive 1. So that carbon now has a positive 1 charge. And so that's the resonance structure. So the true molecule never looks like this, and it never looks like this. It only, ever, always looks like a little something like that. With this bond being something in between a single and a double bond, and there being partial charges on each of the atoms. The fact that it has resonance means that this molecule is more stable and more rigid. Okay, So we've seen the pattern. Anytime you have a pi bond between atoms of different electronegativity, you've got resonance. So you draw the brackets to warn people, and you draw the resonance arrow that tells them take the average of everything inside. Only that is the true structure. And the curved arrow pattern that goes with this is that the pi electrons go onto the more electronegative atom. Notice the oxygen here would have 2 lone pairs in order to get a total of 8 electrons. So to draw the resonance structure, you just copy that structure at first, exactly as it is. And wherever the tail of the curved arrow is pointing, those are electrons that are moving away from there. So erase those. Oops. And wherever the head of the curved arrow is pointing, that's where the electrons are arriving, so you want to draw the electrons in. If the head of a curved arrow is pointing at an atom, then you draw those in as a lone pair. All right, when you calculate the formal charges there, you'll see that the oxygen has a -1 and the carbon here has a +1. And so those are your 2 resonance structures. So the true structure never looks like either one, ever. It only ever looks like the average between the two. So something like this, with a with a bond in between that's somewhere between a single and a double bond, and partial positive charges on the 2 atoms with different electronegativity. Okay. Last but not least, C. In this one, you see a very electronegative atom, nitrogen, oxygen, fluorine, and chlorine. And so and it has a pi bond going to it, so you have this 4th resonance pattern. Just as good grammar, note that the oxygen has 2 lone pairs on it to get a total of 8 electrons. All right, so now what happens with this is that the pi electrons go onto the more electronegative atom. So we'll draw our resonance arrow that tells people take the average of these 2 structures. Now this carbon skeleton here probably looks really weird. That's because it's 2 rings that are being fused. So that's a ring right there. And then on top of it, there's a second bridge. There's like a bridge between the 2 rings. None of that, though, affects the resonance pattern, which has everything to do with the 2 atoms in the pi bond with different electronegativity. So I'm just going to copy it exactly. Okay, so we have our curved arrow. To draw the second resonance structure, anywhere where there's the tail of a curved arrow, those are electrons that are moving away from there, so erase those. Anywhere where there's the head of a curved arrow, that's where electrons are arriving, so draw the electrons in. If the head of a curved arrow points at an atom, the electrons arrive as a lone pair, so that's how you draw them. And if you calculate the formal charges, you'd see this oxygen has a -1, and this carbon has a +1. And if you're having trouble seeing those formal charges, you might go back to previous videos and practice drawing hydrogens in. Draw all the hydrogens in, and then try to find these formal charges. So the true structure is neither one of those. It's the average of the 2, only ever. And the fact that this has resonance at all is telling us that this molecule is more stable and more rigid than it would be if it didn't have resonance. And so that's the 4th pattern, 4th resonance pattern, a pi bond between 2 atoms of differing electronegativity.